So we're looking at page 135. Number 1, part A. Part A reads, write the volume V of a cube as a function of the side length S. So we should all know, if not, you probably quickly look it up, just Google it.
You know how it is, and then like if the cube expanded, like how that.
Yeah, that's what I thought.
We're just writing the equation for cube. No, but last year we did something similar to this, and then we had to find out how much.
I think it is related to that.
Is it? Do you remember that?
Related
And
to
I hated
that.
that. That was the mistake.
Oh, yeah.
Okay, guys. Focus. Okay, any questions about this volume of a cube, S cubed?
No.
Right, we have a quick visual. One of these side lengths is up. Okay, so part B says, find the instantaneous rate of change of the volume with respect to a side S. Okay. So because this is written the way it is, that it's V in terms of S.
It's
we can,
dv.
Yep, we can think about taking the derivative of this, which would be 1. And what I'm actually, the way I'm going to show it to you is going to be good for moving forward.
Why do you have the 1 there?
It's like
ds.
you just said, taking the derivative.
So it's
Derivative of the
1
side.
Wait, where did the?
per change or times change in V equals 3s squared change in S.
Where does d equal change? You couldn't change it.
I think he's showing you how, he's showing you how you get there.
I just not following it.
And then we divide both sides by ds, and dv ds
Oh, I see. Okay, yes, sorry.
would be equal to 3s squared.
I guess.
So let's understand that for this particular problem, we can go straight from here to here. That's fine because it's written literally for V and all in terms of S. That's fine. I'm showing you something that is going to come in handy when we start looking at, say, the idea of partial derivatives, which will come in later. But for right now, you can go right from here to here. That's fine. Did not do this to confuse you, but it will come in. It will come handy later. But you could go from here to here as well. But if you're fine going from here to here, that's fine too. But for right now, go from here to here if that makes you feel comfortable. So this is the instantaneous rate of change of the volume with respect to a side S. Okay? So we can see how the volume is changing, say, at 1 second, at 2 seconds, at 3 seconds, so forth. So logically, as time goes on, the rate of change of the volume is increasing. Right, we see that? So the rate of change of the volume, say when S is 2, would mean that the volume is changing at a rate of 12 cubic, whatever it is, cubic inches. Here it's
Inches, cubes, over
do they give us a unit? Inches? Yeah, inches. So at 2 seconds, yeah, 12 cubic inches per second. Oh, sorry, not seconds. Side length. 12 cubic inches per inch.
Yeah.
So this is just, I'm just discussing number 1, which may lead into C.
Wait, can you say that?
Yeah, this is going to tie into part D. But I'm just saying that as the side length increases, so I'm going to say as the side length increases, the rate of change of the volume increases. You can see that here, right? This is, you imagine it's a parabola, concave up.
Because if like side length is 1, then it's going to be just 3.
Yeah.
If it's 2, then it's going to be 12.
Yeah, so let's be specific. Yeah, so the rate of change of the volume it's going to be when S is 1, it's going to be 3 cubic inches per inch. And then, for example, if when the side length is 3 inches, then we know the rate of change of the volume will be 27 cubic inches per inch at that when the side length is 3 inches.
Now, how does this tie into what we did on Monday?
What was Monday?
Monday was,
Happy birthday.
what did we do Monday?
Didn't we do instantaneous rate of
But actually, the physics, like,
Let's not worry about how this ties into else. This is strictly the relationship of volume of a cube to its side length.
Oh, this is what we did for that
This is what we
section,
did
so it has
in
to
the
tie
fourth
in.
class. No, like, I understand how we're doing all this, but I just seem so.
It ties in because it deals with derivatives. We were talking about instantaneous rate of change or something. Okay.
It was a throwing thing, it's displacement.
Oh yeah, rate of change. This is rate of change. Yeah. So the 3s squared is the rate of change.
3s squared is the rate of change, the instantaneous rate of change of the volume with respect to the change in the side length. I'll write that. So what that means, the terminology is clear.
Literally.
Instantaneous rate. Instantaneous rate of change of the volume with respect to
Did not like.
no, it was not cooperating. With respect to change in side length. That's how we can think of this dVds. The instantaneous rate of change of the volume with respect to change in side length. D is like instantaneous change. Instantaneous change.
Yeah, something like that.
So, part C, it says evaluate the rate of change of V at side length equals 1 and side length equals 5.
75.
So, in other words, find V prime of 1 and V prime of 5. Remember, V prime is another way of writing dVds. It's another notational thing, another same notation. And this would, of course, equal to 3. And then to find V prime of 5, that would be equal to 3 times 5 squared, which is 75. Just using this here. So this can also be thought of as V prime of S. Another way of saying V prime of S, dVds.
Right.
Any questions?
Nope.
And then now part D says if S is measured in inches and V is measured in cubic inches, what units would be appropriate for dV ds? And it actually would just be cubic inches per inch, because that is the units that are changing. The units that's changing is cubic inches per inch. So don't think about doing it necessarily with the units. Think about bringing the 3 down. It's not necessarily true. So let's go ahead and I think I did one of those. Probably on one. Let's see. You can see this. That's okay. I know.
Right, it's like inches cubed over inches, so you would think that the inches on the bottom would cancel out one of the inches on the top.
Yeah, but
It's like that.
we want to think of this as like a notational thing, like
Okay.
what it reads as.
Okay.
Like
It should be like a raster.
inches cubed per inch is kind of how we want to think about that.
Okay. Okay. Sounds good.
Like MPH.
Yeah. So like if you're using for something, the units are different, but in this case, it's both inches. Yeah. It's like,
So you can think of this as cubic inches per cubic inches
We'll just do it just cubed.
per inch. That's how we can think of this.
yeah.
Any other questions on one? Three. 3 says, write the area A of an equilateral triangle as a function of the side length S.
I didn't really understand, I mean, I understand what's asking, I don't understand how you got.
I completely forgot.
Yeah. So let's visualize what an equilateral triangle looks like.
It looks halfway tight.
Yeah, I was very.
All the sides are all the same.
Right? So this we have S, S, and S. So let's imagine if we know that the area of any triangle is 1/2 pH.
But if you're doing the area of equilateral.
So let's think about this. Let's see if we can find out how could we find. Is there a way to express the height of this
H.
in terms of S?
It's a 36.
Aha, good job. It's a 3690.
That
So
just makes so much more sense.
we think about. There's definitely this is a good example. Part of the reason I choose these problems is because I want you guys to sketch something on paper. I want you to write down what you know and then see if we can make a connection. So we know that this is a 30, 60, 90. And so what would this length here be?
1/2 S.
Very good, 1/2 S. Good. And then now let's see if we remember our ratios here. This is one of those fundamental things that you learn in trig or pre-calc that kind of sticks around, the 45-45 and the 30-60.
3. Square root of 3 over 2.
So yeah, we know that this is twice this,
So 1.
and this guy is what, square root of 3 times larger than this?
Well, isn't that like S?
So this should be square root of 3 over 2 S. Right? Because this is, in case you know, we can go ahead and write the regular guy, right? If this is X, this is 2X, and this guy here is square root 3X. Yeah. So using this, so the area is equal to 1/2 base times height. So 1/2, the base of this triangle is S. And the height of this triangle, we definitely know is square root 3 over 2x. So now we got what we want. We got, and just simplify it, we got something that's all in terms of S. They wanted to express this strictly as in terms of the side length S, yes.
When I kind of looked at this, I thought Pythagorean theorem.
Okay.
And I got the. So,
Okay, so that's good. So understand that if you did do Pythagorean's theorem, you should arrive at the same exact value. Right? Because Pythagorean's theorem, it holds true for all right triangles. We know this is S, we know this is 1/2 S, so Pythagorean's theorem should also let us solve it this way. So that's good. So either tool that you use, it doesn't matter. Good point. So this squared plus whatever this is squared should be this squared. And we come up with this as well.
I got a different equation.
Okay, so let's see. Let's go ahead and do Pythagorean's
So I
theorem.
kind of screwed it up, which is highly likely.
So let's do this. It's possible I could have very easily made a mistake. So let's take. Doesn't really quite do it that way. I want to put it on a separate page or not. I really don't want to.
I might have used the wrong thing.
Let's
in
do
all
this.
honesty.
Let's do this. Let's do or Pythagorean's theorem. Just I'm curious, right? It should be the same. What are you doing?
Sorry.
Going away.
It wouldn't work.
So Pythagorean's theorem, it wouldn't work.
I don't think so because I actually found.
It better work. It should work. It better, right? Pythagorean's theorem works for all right triangles. It should work. So let's see. Let's see. So 1/2 S squared plus the unknown, we'll call it B squared, should equal S squared. So 1/2 squared, so 1/4 S squared plus B squared should equal S squared. So B squared, if I subtract 1/4 S squared from both sides, I should have 3/4 X squared, and if I square root both sides, and of course I'm only concerned about the positive root, I don't care about the negative, we're talking about distance or reality, just the positive. The square root of this, the square root of, and again, just the positive, 3/4 X squared. If we go at the square root of 4, works out nicely, right? It's the 1/2 that can come out the front. So this would in fact definitely come out to square root of 3 over 2s.
Okay, I just did my things wrong. I just screwed up with when I was doing it. That's awesome. Cool.
Okay. So that being said, you should definitely keep note of these though, in case we have something that we need to figure out where we only know one of the sides and we know it's 36, but here we happen to know 2 of the sides of the right triangle, so we can definitely easily just done Pythagorean's theorem. Let me go ahead and put a divider here to show that you don't have to do both of these when you're reviewing this. That's just kind of like an or thing or anything. Or we can do this. That makes it clear. And of course, this guy simplifies. What we end up getting is square root 3 over 4 S squared for the area.
Oh, you just multiplied that back in again.
Yeah, I just simplified this. Yep.
Yeah, that makes sense. I was just like,
Another way this can be thought of is you can think of it as A of S. Again, maybe it's kind of like helping you see, okay, as a function of S, right? So I could write this as, but this can be written same exact meaning to say A of S. It's back to that whole notation thing. We're starting to know, especially calculus, there's slightly different ways of saying the same thing. This is a little more detailed, but the same exact meaning. Same meaning. This is a little more detailed. It's specifying what the independent variable is. Specifying, okay, A as a function of S. Same thing.
Coolio.
Any questions thus far in here? No? So then number 3, part B. We got probably time to do part B. We found out that A of S is equal to square root of 3 over 4 S squared. want you guys to realize, again, the meaning behind this, what this is saying is that you could tell me the area of a equilateral just based on one of the side lengths. So then if we go one step further and we go a prime s, the shortcut for polynomials 2 to the front, which will give us square root 3 over 2s. So when we find the derivative of the shortcut, the 2 comes to the front, so 2 times square root 3 over 4 is square root 3 over 2, because of the 2 and the 4 simplify. And then we have s is left over, drop down a power, and that's it. And so square root 3 over 2s happens to be height. Yeah. Just looks like a coincidence. Okay, so what does this statement mean here? This statement means here that you can tell me at any point how quickly the area is changing just with respect to what the side length is at any point. So let's say we were to blow this up, this is like an image or something, we were to blow it up and make it a bigger triangle. You could tell me at any point in time, or not any point in time, for any side length s, you could tell me how quickly the area is changing. Let's write that, we'll finish with that. And this is how quickly the area is changing with respect to change in the triangle's side. That's what this is saying. How quickly the area is changing with respect to change in the triangle's side.
Are we still going to go for number 6?
Of course.